In the autumn of 1974, inside a control room at the Stanford Linear Accelerator Center, a research group led by the physicist Martin Pearl sat in front of stacks of printouts from a detector called Mark I. The detector sat at the heart of a machine called SPEAR, a ring where electrons and their antimatter twins, positrons, were sent around in opposite directions and smashed together at the center. Most of what came out of those collisions was familiar and expected, the well-behaved debris of known particles going about their known business. But scattered through the data were a small number of events that refused to make sense. An electron would come flying out of the collision point in one direction, and a muon, a heavier relative of the electron, would come flying out in another. No photons, no obvious missing pieces that could be explained by particles already on the books. Just an electron and a muon, born together from nothing anyone could yet name. Pearl and his colleagues counted 24 of these strange pairings. They checked their equipment. They checked their assumptions. They tried, for months, to explain the pattern using particles already known to exist. And they failed. What they were looking at, though they did not yet have the language for it, was the shadow of a new kind of matter, heavier than anything like it ever observed, appearing for a fraction of an instant and then vanishing before it could be caught directly. That shadow would eventually be given a name drawn from the Greek word for third, because it was the third charged particle of its kind found in nature after the electron and the muon. It would be called the tau. This is a program about that particle, and about a question that sounds almost childishly simple until you actually try to answer it. What is a tau particle made of? The honest answer takes a while to unfold properly, and it touches nearly every part of how physicists currently think matter is put together. It is worth spending real time on, not because the tau itself plays some starring role in the visible universe, but because it is one of the clearest windows available into what a fundamental particle actually is, as opposed to what our intuition, built on a lifetime of handling solid objects, expects it to be. The tau is heavy. It is unstable. It is, in the modern description, not built out of smaller pieces at all. Understanding why physicists say that and how they came to measure a thing so short-lived is the subject of the next several sections. The tau also matters for a more practical reason, one that has kept it under active study for 50 years, rather than filing it away as a historical curiosity once its basic properties were pinned down. Precisely because it is the heaviest of the three charged leptons, the tau is unusually sensitive to certain kinds of new physics that lighter particles would barely register. In many proposed extensions of the Standard Model, hypothetical new particles or forces coupled to matter in proportion to mass, meaning any small deviation from the Standard Model's predictions would tend to show up first, and most clearly, in measurements involving the tau rather than in the electron or muon. That is part of why experiments continue to measure its mass, its lifetime, and its decay patterns to ever finer precision, and why the tests of lepton universality discussed later in this program focus so heavily on comparing the tau's behavior against its lighter relatives. A particle that plays no role in ordinary chemistry or biology can still be one of the most useful tools available for testing whether the current picture of physics is complete. To place the tau properly, it helps to start with its more familiar relatives because the tau does not exist in isolation. It is the last and heaviest member of a family of three. And that family structure is itself one of the more puzzling regularities in nature. The electron needs little introduction. It carries a single negative electric charge. It has almost no mass by the standards of everyday matter. And it is the particle responsible for chemistry, for the flow of current in a wire, and for the outer structure of every atom in your body. Its mass corresponds to an energy of about 511,000 electron volts, a unit particle physicists use because volts and joules become awkward at this scale. The electron was identified in 1897 by the physicist J. Thomson, working at the Cavendish Laboratory in Cambridge, through experiments with cathode rays, and it has been studied more precisely than almost any other particle since. Roughly 40 years after the electron was identified, a second, heavier particle turned up, again somewhat by accident, in studies of cosmic rays, the steady rain of high-energy particles that strikes the upper atmosphere from space. In 1936, Carl Anderson and Seth Nettermeyer, working with cloud chamber photographs at Caltech, found tracks that curved in a magnetic field the way an electron's track would curve, but that penetrated matter far more easily than an electron of the same energy should. The particle responsible carried the same negative charge as the electron and behaved, in almost every measurable respect, like a heavier copy of it. It came to be called the muon, and its mass corresponds to about 106 million electron volts, roughly 207 times the mass of the electron. Muons are unstable, decaying after an average of about 2/millionths of a second into an electron and a pair of neutrinos. But that is a comparatively long lifetime by the standards of particle physics, long enough that muons produced by cosmic ray collisions high in the atmosphere routinely survive the trip down to sea level. On a typical day, roughly 1 muon passes through an area the size of an open hand every second at ground level, a flux that was itself one of the early confirmations of time dilation in special relativity, since a muon, moving at close to the speed of light, lives from the perspective of an observer standing still on the ground, long enough to complete a journey that its own internal clock experiences as much shorter. When the muon's existence became clear, the physicist Isidore Rabi is reported to have asked a question that has stuck in the field ever since. Who ordered that? Nothing about the chemistry, biology, or everyday physics of the world seemed to require a heavier copy of the electron. It simply appeared because the underlying mathematics of the universe, whatever it turns out to be, evidently permits it. The tau is the next entry in that same pattern, discovered nearly 40 years after the muon, and it raises Rabi's question again with even more force, because the size of the jump this time is so much larger. Its mass corresponds to about 1,777,000,000 electron volts, which places it close to 3,500 times the mass of the electron, and nearly 17 times the mass of the muon. In terms of pure numerical weight, if the electron is treated as 1 part, the muon is about 200 parts, and the tau is roughly 3,500 parts. There is no known chemical, biological, or everyday physical process that calls for a particle this heavy in this particular role. It does not build stable atoms. its mass is too large and its lifetime too short for it to participate in ordinary chemistry at all. And yet, the equations that describe the electron and the muon apply to it as well, with the same electric charge, the same intrinsic angular momentum physicists call spin, and the same set of interactions, only carried by something dramatically heavier. This three-part structure, a light first generation making up ordinary matter, a heavier second generation appearing mostly in cosmic rays and accelerators, and a still heavier third generation appearing almost exclusively in high-energy experiments, is repeated among the other fundamental particles that make up matter as well. The up and down quarks that build protons and neutrons have heavier cousins called the charm and strange quarks, and heavier still, the top and bottom quarks. Each of the three charged leptons, the electron, the muon, and the tau, is paired with its own nearly massless neutrino. Physicists refer to this arrangement as three generations of matter, and while the pattern itself is precisely described by the mathematics of what is called the Standard Model, the theory that currently organizes nearly everything known about particles and their interactions, the reason there are exactly three generations rather than one or five or some other number is not something the Standard Model explains from first principles. It is a measured fact, built into the theory as an input, not derived as an output. That gap between what is measured and what is understood from deeper principles will come up again later in this program, because it sits at the center of what remains genuinely unresolved about particles like the tau. Before going further into what the tau actually is, it is worth being precise about a word that gets used constantly in this kind of discussion, and that is easy to slide past without noticing how strong a claim it makes. That word is fundamental. In ordinary language, calling something fundamental usually just means it is important or basic. In particle physics, the word does a much more specific job. A particle described as fundamental is one that, as far as current experiments can tell, is not made of anything smaller. It has no internal parts. It is not a container holding other particles the way a proton contains quarks. The proton, in fact, makes a useful contrast here. When physicists at facilities like SLAC in the late 1960s fired high-energy electrons at protons and studied how the electrons scattered, the pattern of scattering revealed that the electrons were bouncing off smaller, hard structures inside the proton rather than off one smooth object. Those structures were later identified as quarks, bound together by carriers of the strong nuclear force called gluons. The proton, in other words, has an inside. It has architecture. Its mass comes overwhelmingly from the energy of that internal activity, the quarks and gluons in violent continuous motion, rather than from the quark's own masses, which are individually quite small. That discovery of the proton's internal structure was itself the product of a long series of experiments, beginning in the late 1960s at SLAC, the same laboratory where the tau would later be found, and it earned Jerome Friedman, Henry Kendall, and Richard Taylor the Nobel Prize in Physics in 1990 for confirming what became known as deep inelastic scattering, the technique of probing a particle's internal structure by firing something at it energetically enough to resolve details smaller than the target itself. The technique works because higher energy corresponds, through the mathematics of quantum mechanics, to shorter wavelength, and shorter wavelength is what is needed to resolve fine spatial detail, in much the same way a microscope needs shorter wavelength light to see smaller objects. The proton's internal quark structure only became visible once electron beams reached energies high enough to probe distances well below the proton's own size. The tau has been probed in exactly this same experimental spirit, using high-energy collisions and precision measurements of how it behaves under electric and magnetic fields, and no equivalent internal structure has ever shown up. Every measurement to date is consistent with the tau being what physicists call a point particle, meaning that within the limits of current instruments it has no measurable size at all. Those limits are not vague. Experiments studying how electrons, muons, and taus scatter off other particles at high energy, particularly at the LEP collider at the European laboratory CERN through the 1990s, found no deviation from point-like behavior down to distances on the order of 1,000th of a trillionth of a meter, a scale about 1,000 times smaller than the proton itself. The logic behind this kind of measurement is the same logic Ernest Rutherford used in 1911 to discover the atomic nucleus, firing a beam of particles at a target and watching for any unexpected scattering that would signal a hard, compact structure hidden inside. At LEP, the target and the beam were both leptons, colliding at energies far higher than Rutherford ever had available, and the pattern of scattering that came out matched to a high degree of precision what theory predicts for a collision between two dimensionless points. No hint of a hard core, no unexpected clustering of scattering angles, nothing to suggest that tau has an inside worth probing further, at least not at the distance scales these experiments can currently reach. That is not proof that the tau has literally zero size in some final, absolute sense. It is a statement about the resolution of the best instruments built so far, and it should be read that way as a measured limit rather than a metaphysical certainty. But within that limit, the tau behaves as a structureless point, an object defined entirely by a small set of quantum numbers, mass, charge, and spin, rather than by any spatial extent. This is genuinely one of the harder ideas in this whole subject to sit with, because it runs directly against how a lifetime of handling solid objects trains a person to think. Ordinary intuition says that if something has weight, it must have some amount of stuff packed into some amount of space, and the more it weighs, the more stuff, or the more tightly packed, that stuff must be. The tau does not fit that picture, and neither does the electron, or the muon, or the quarks, or any of the other particles the Standard Model classifies as fundamental. Their mass is not a property of contained material. It is closer to being an intrinsic label, a number written into the particle's identity, and where that number actually comes from is a separate question, one physicists have made real progress on, but have not fully closed. That question, where mass comes from for a particle with no internal structure to weigh, leads directly to one of the most important developments in 20th century physics, and one that connects unusually well to the tau specifically. For most of the history of the Standard Model, there was a genuine puzzle sitting underneath the whole framework. The equations that describe how particles interact through the electromagnetic and weak nuclear forces work most naturally if the particles involved are massless. Simply inserting mass terms for the electron, the muon, the tau, and the force-carrying particles called the W and Z bosons by hand breaks the mathematical consistency of the theory. Physicists needed a mechanism that could give these particles their observed masses without wrecking the underlying structure. The solution, proposed independently by several theorists in the 1960s, including Peter Higgs, François Englert, and Robert Brute, involves an idea now called the Higgs field. A field, in this context, is not a substance but a property assigned to every point in space, in something like the way temperature can be assigned to every point in a room, except that the fields relevant here are quantum mechanical, and their excitations, ripples above their lowest energy state, are what get observed as particles. The electron, the muon, and the tau are each understood as excitations of their own distinct field, permeating the entire universe. The strength with which a particular field couples to the Higgs field is often called its Yukawa coupling, a term named after the physicist Hideki Yukawa, whose earlier work on the theory of nuclear forces provided the mathematical template later adapted to describe how fields interact with each other in this way. The Higgs field is described as a field that fills all of space and that, unlike most other quantum fields, does not settle to zero even in its lowest energy state. Every point in the universe sits within this non-zero background field. Particles that interact with it experience something like resistance as they try to move or change speed, and that resistance is measured in practice as mass. Crucially, different particles interact with the Higgs field by different amounts through what is called a coupling strength, and the strength of that coupling is what determines how heavy a given particle turns out to be. The electron couples weakly and is light. The muon couples more strongly and is heavier. The tau couples more strongly still and is heavier again. The pattern of masses across the three generations is, in this framework, really a pattern of coupling strengths to the same underlying field, rather than three unrelated facts about three different objects. It is worth being careful about how much of this is measured and how much is modeled, because the two get blurred easily in popular explanations. The existence of the Higgs field itself and its associated particle, the Higgs boson, was confirmed experimentally in 2012 when the ATLAS and CMS collaborations at the Large Hadron Collider at CERN independently announced the discovery of a new particle consistent with the long-predicted Higgs boson. That is a measured result. The claim that the Higgs field is specifically responsible for the mass of particles like the tau required a further, more difficult measurement, because it is one thing to find the Higgs boson and another to show it actually couples to a given particle in the way theory predicts. That further evidence came in 2017 when the CMS collaboration published direct observation of the Higgs boson decaying into a pair of tau particles, a result the ATLAS collaboration confirmed shortly after, with a combined analysis from both experiments strengthening the case further. This was significant specifically because the tau is the heaviest lepton, and the Higgs boson's tendency to decay into heavier particles more readily than lighter ones is exactly what the coupling-based picture of mass predicts. Watching the Higgs boson decay into taus at the rate expected was strong direct evidence that the mechanism responsible for the tau's mass is the one theory describes. What is not yet explained, and this is the important caveat, is why the coupling strengths take the particular values they do. Theory can describe how the electron, the muon, and the tau acquire mass through their interaction with the Higgs field. It does not currently predict, from more basic principles, why that interaction should be roughly 3,500 times stronger for the tau than for the electron, rather than some other ratio entirely. This unexplained pattern of coupling strengths across the three generations is sometimes called the flavor puzzle, and it remains one of the open questions in particle physics, one this program will return to near the end. With the question of mass addressed as far as current physics allows, it is worth turning to a second property that is, if anything, even harder to picture intuitively for something with no size at all, and that is spin. In everyday language, spin means rotation, a wheel turning on an axle, a planet turning on its axis. Fundamental particles are described as having spin too, measured in specific fixed units, and the tau, like the electron and the muon, has a spin value of 1/2, expressed in the natural units physicists use for angular momentum at this scale. One of the more precise ways physicists test whether a particle is behaving exactly as theory predicts is by measuring what is called its magnetic moment, a number describing how strongly the particle's intrinsic spin interacts with an external magnetic field. For the electron, this quantity has been measured and calculated to better than 1 part in a trillion, making it one of the most precisely tested predictions in the entire history of science. And the two numbers, measured and calculated, agree to that same extraordinary precision. For the muon, a long-running experiment at Fermilab, building on earlier work at Brookhaven National Laboratory, has measured the equivalent quantity to similarly high precision, and comparing that measurement against theoretical calculations has become one of the more closely watched tests in particle physics, with some tension between the measured value and certain theoretical calculations still being actively worked through as of this program. For the tau, no comparably precise measurement exists at all, and the reason comes directly back to its lifetime. A magnetic moment measurement of this kind requires watching a particle's spin precess, or gradually rotate over many cycles while it sits inside a magnetic field, something that takes far longer than 290 femtoseconds to observe directly. Physicists have instead had to rely on indirect methods, inferring bounds on the tau's magnetic moment from the way tau pairs are produced and decay inside collider detectors, methods that so far have only been precise enough to confirm that the tau's behavior is broadly consistent with theoretical expectations, without yet reaching anywhere near the extraordinary precision achieved for the electron or the muon. Closing that gap remains one of the concrete, well-defined technical goals of current and planned tau physics programs, including the work underway at Bell 2. The obvious question is how something with literally no spatial extent, no surface, no axis, can be said to be spinning in any physical sense. And the honest answer is that it cannot, at least not in the way a top or a planet spins. Quantum spin is an intrinsic property present from the moment a particle exists that behaves mathematically like angular momentum and that produces measurable effects such as a magnetic moment that are entirely consistent with genuine rotation. But it does not correspond to physical rotation of a spatially extended object because the particle is not spatially extended. It is better understood as a fixed quantum number, a label the particle simply carries that happens to interact with magnetic fields the way rotating charge would. Physicists use the word spin because The mathematics of quantum angular momentum was worked out using the same tools originally developed to describe rotation, and the name stuck even once it became clear the underlying picture is not literally rotational for a point particle. This is a case where the vocabulary of physics carries some historical baggage that can mislead a listener trying to build a mental picture, and it is worth naming that plainly rather than glossing over it. It is worth pausing briefly on what those interactions actually are, since they have been mentioned without much explanation so far. Physics currently recognizes four fundamental forces. Gravity, familiar from everyday experience, is by far the weakest of the four at the scale of individual particles and plays essentially no measurable role in particle physics experiments. The strong nuclear force binds quarks together inside protons and neutrons, and binds protons and neutrons together inside atomic nuclei, but it does not act on leptons like the tau at all. The electromagnetic force governs the attraction and repulsion of electrically charged particles, and the tau, carrying a negative charge, feels it in the same way the electron and muon do. The weak nuclear force is the least intuitive of the four, responsible for processes that change one type of particle into another, including the radioactive decay of certain atomic nuclei, and, centrally for this program, the decay of the tau itself. Unlike the other three forces, the weak force is carried by particles, the W and Z bosons, that are themselves extremely massive, which is part of why weak interactions tend to happen so much more slowly, or in the tau's case, so much more briefly, than electromagnetic ones. Between its mass, its spin, and its electric charge of -1, the tau is essentially fully specified. Those three numbers, along with the way it interacts with the electromagnetic force, the weak nuclear force, and, unlike quarks, not at all with the strong nuclear force, are the complete description. There is no additional internal machinery to catalog. The description feels sparse compared to what intuition expects from something this massive, and that sparseness is, again, precisely the point this whole subject keeps returning to. A fundamental particle in the modern description is not a small object with properties. It is closer to being a bundle of properties, full stop. Having established what the tau is in the structural sense, it is worth returning to the story of how it was actually found, because the discovery itself is a good illustration of how difficult it is to pin down a particle this short-lived, and how much careful, incremental work stood behind the eventual announcement. Martin Pearl's group at SLAC began their search in the early 1970s, using the newly built Spear Collider, a ring roughly 230 meters around, built at the SLAC site in Menlo Park, California, which brought electrons and positrons into head on collisions at energies that could be tuned across a range of several billion electron volts. It is worth noting the scale of these machines, since it is easy to lose sight of just how much engineering sits behind a result described in a single sentence of a physics paper. Spear itself was a modest machine by later standards, but the tradition it began led directly to the Large Hadron Collider, a ring 27 kilometers in circumference straddling the border between France and Switzerland, cooled to a temperature colder than deep space to keep its superconducting magnets operating, and capable of accelerating protons to within a fraction of a percent of the speed of light before bringing them into collision. Facilities on this scale are what make it possible to concentrate enough energy into a small enough space to produce particles as heavy as the tau in usable numbers, and the fact that a heavy, structureless point particle, first inferred from 24 anomalous events in 1974, is now produced and measured routinely in large samples at some of the most complex machines ever built, is itself part of the story of how thoroughly that original inference has since been confirmed. When an electron and a positron annihilate at these energies, the collision can, in principle, produce any particle or pair of particles allowed by the laws of energy conservation and the relevant conservation rules, including pairs of new, as yet undiscovered particles, provided the collision energy is high enough to create their mass. Pearl had proposed, as early as 1971, that a heavier lepton might exist and might be detectable through exactly the kind of anomalous electron-muon pairs his team eventually found. The theoretical case was strengthened by work from Young-Soo Tsai, a theorist at SLAC, who worked out in detail what the signature of such a particle's production and decay would actually look like in a detector, giving the experimental search something concrete to look for. The signature itself required an unusual kind of indirect reasoning, because the hypothetical heavy lepton, if it existed, would be so short-lived that it could never reach the detector itself. It would have to be inferred entirely from what it decayed into. The proposed process worked like this. An electron and a positron annihilate and produce a pair of the new heavy leptons, one particle and one antiparticle. Each of these new leptons then decays almost immediately, through the weak nuclear force, into a lighter charged particle, along with invisible neutrinos that carry away some of the energy without being directly detected. If one of the pair happened to decay into an electron and the other into a muon, the detector would record an event with exactly one electron and exactly one muon coming from the collision point, no other charged particles, and an apparent imbalance in the total energy and momentum, because the neutrinos escaped unseen. This was a distinctive enough pattern that it could not easily be faked by any combination of already known particles and their established decay processes. The search itself required patience, because the production rate depended heavily on the collision energy chosen, and the right energy was not obvious in advance. Spear could be tuned across a range of center of mass energies, and Pearl's group spent long stretches of running time at different settings, gradually mapping out where the anomalous electron-muon pairs became more common. The most productive data came from running at an energy of about 4,800,000,000 electron volts, comfortably above the threshold needed to produce a pair of particles with the mass size calculations suggested, roughly between 1,600,000,000 and 2 billion electron volts each. By late 1974, Pearl's team had accumulated a data set showing 24 events fitting this exact pattern, at a rate too high to be explained as background noise or misidentified particles from known physics. The team published their result in December 1975 in a paper titled Evidence for Anomalous Lepton Production in the Electron-Positron Annihilation. The paper was careful in its language, presenting the anomalous events and noting that they were consistent with the production and decay of a new heavy lepton with a mass somewhere between about 1,600,000,000 and 2 billion electron volts, without yet claiming a definitive discovery. That caution was well placed and also short-lived. Over the following several years, other groups working at Spear and elsewhere found additional decay channels of the same new particle, including combinations involving hadrons, particles built from quarks, which matched the predictions for a lepton heavy enough to decay into them, something the electron and muon are too light to ever do. By 1977, the accumulated evidence across multiple decay channels and multiple experiments had converged firmly on a single, consistent picture, and the particle's existence was accepted by the physics community as established. It was named the tau from the Greek letter used to represent it, itself chosen to echo the Greek word for third. Martin Pearl received the Nobel Prize in Physics in 1995 for the discovery, sharing the award that year with Frederick Rains, who was honored separately for the earlier detection of the neutrino. The measured mass that came out of this decades-long confirmation process, 1,777,000,000 electron volts, sits almost exactly at the value Pearl's original 1975 paper had estimated from those first 24 events, a fact that speaks to how carefully that initial inference had been reasoned through, even though the particle itself could never be observed directly. The method used to find the tau, inferring a short-lived particle entirely from its decay products, becomes even more central once the discussion turns to the tau's lifetime, because the tau does not merely decay quickly. It decays on a timescale that makes even the muon, its intermediate cousin, look almost stable by comparison. The tau's mean lifetime has been measured with high precision, most recently through experiments at electron-positron colliders that produce large numbers of tau pairs and track their decay points with fine spatial resolution. The current best measured value is about 290 femtoseconds. A femtosecond is a unit equal to a millionth of a billionth of a second, meaning the tau exists, on average, for a span of time so brief that a single second contains roughly the same number of tau lifetimes as there are seconds in about 100,000 years. Even traveling close to the speed of light, a tau particle covers only about 87 millionths of a meter, thinner than a human hair, before it decays, if measured in its own rest frame. In real collider experiments, tau particles are typically produced with enough energy that relativistic time dilation stretches this out considerably from the point of view of the laboratory, allowing them to travel measurable distances of a few millimeters before decaying. And that stretched, boosted decay length is in fact one of the key signatures experiments use to identify tau production events among the flood of other collision debris. Both descriptions are correct. The particle's own internal clock, so to speak, runs for about 290 femtoseconds, and what an outside observer measures depends on how fast the particle is moving relative to them, exactly as special relativity predicts and as these experiments confirm on a daily basis. Why does the tau decay so quickly in the first place? The short answer is that it is heavy, and in particle physics, heavy and unstable tend to go together whenever a lighter set of particles exists that the heavier one is allowed to decay into. The relevant force here is the weak nuclear force, the same force responsible for radioactive beta decay and for many of the transformations that change one type of particle into another. Through the weak force, a tau can transform into a lighter charged particle, either an electron or a muon, along with a pair of neutrinos, one tau neutrino and one neutrino matched to whichever lighter lepton it produced, a combination required by a conservation rule that keeps the overall count of each lepton type balanced across the transformation. Mechanically, this proceeds through the brief appearance of a W boson, the massive, electrically charged carrier of the weak force mentioned earlier. The tau converts into a tau neutrino and an intermediate W boson, and that W boson, existing for an even shorter interval than the tau itself, then converts into whichever lighter particle and neutrino pairing the decay ultimately produces. The entire sequence happens far too quickly to be observed in stages. What a detector actually records is the tau's decay products appearing at a single point in space, and the two-step process involving the W boson is reconstructed from theory and confirmed statistically. By checking that the overall rates and angular patterns of the observed decays match what that two-step process predicts, rather than by watching the intermediate step occur directly. This purely leptonic channel accounts for a bit over a third of all tau decays, split roughly evenly between the electron and muon outcomes. Within that leptonic third, the split is close to even, with about 17 out of every 100 tau decays producing an electron, a tau neutrino, and an electron antineutrino, and a nearly identical 17 out of every 100 producing a muon, a tau neutrino, and a muon antineutrino. The small difference between the two channels traces back almost entirely to the muon's larger mass compared to the electron, which very slightly restricts the amount of leftover energy and momentum available to share among the decay products. The remaining decays, making up close to two-thirds of the total, go through hadronic channels, meaning the tau decays into one or more particles built from quarks, typically pions, along with a tau neutrino. The single most common individual outcome, accounting for a bit more than a quarter of all tau decays, produces one charged pion, one neutral pion, and a tau neutrino. A further tenth of all decays produce just a single charged pion and a tau neutrino, with no accompanying neutral pion at all. Beyond these two dominant channels, smaller fractions of tau decays produce three charged pions, sometimes with an extra neutral pion added, each channel progressively rarer as the number of particles that have to be produced together and the energy that has to be divided among them increases. This hadronic option is available to the tau specifically because it is heavy enough. Its mass exceeds the combined mass of a pion and a neutrino by a wide enough margin that the decay is allowed by energy conservation, whereas the much lighter electron and muon simply do not have enough mass energy available to produce even the lightest hadrons, and so are forbidden from decaying that way. This is part of why the tau is sometimes described in technical literature as the only lepton heavy enough to decay into hadrons, a distinction that makes it an unusually useful subject for testing certain predictions about how the weak force and the strong force interact, since its decays offer a clean, well-controlled laboratory for hadronic physics that the lighter leptons cannot provide. Every one of these decay paths, leptonic or hadronic, produces a tau neutrino as part of the outgoing debris, and that detail points toward the last major piece of this story, because the tau neutrino itself has its own separate and much longer discovery history. The existence of a distinct tau neutrino, as opposed to the neutrino types already associated with the electron and the muon, was strongly implied by the pattern of tau decays observed in the years following the particle's discovery, and it fit naturally into the three-generation structure of the Standard Model. But implication is not observation, and neutrinos are notoriously difficult to observe directly under any circumstances. They carry no electric charge, they do not feel the strong nuclear force, and they interact with ordinary matter so weakly that the overwhelming majority pass through the entire Earth without any interaction at all. Confirming that a distinct tau neutrino actually existed rather than assuming it from theoretical consistency took until the year 2000, a full 25 years after the tau lepton itself was found. The experiment responsible was called DONUT, an acronym for Direct Observation of the New Tau, run at Fermilab, the Fermi National Accelerator Laboratory outside Chicago. The collaboration used Fermilab's Tevatron accelerator to produce an intense beam containing, among other particles, tau neutrinos, generated indirectly through the decay of heavier particles created in proton collisions with a fixed target. This beam was then aimed at a detector built from alternating layers of iron plates and photographic emulsion, a material that records the tracks of charged particles passing through it in fine enough detail to be scanned and reconstructed in 3 dimensions. The signature the DONUT team was looking for was specific and hard to fake. On the rare occasion that a tau neutrino interacts with a nucleus in the iron, it can produce a tau lepton directly, and that tau lepton, in turn, decays almost immediately into other particles, producing a visible kink in the particle track, a sudden short-lived detour before the track continues as something else. Finding that kink and confirming it matched the expected signature of a tau decay, rather than some other process, was the direct evidence needed. The scale of the effort involved is worth stating plainly, because it illustrates just how rare these interactions are. The Fermilab beam produced roughly 600 million particle interactions in the emulsion target during the run. From that enormous set, the collaboration narrowed the candidates down to about 1,000 events worth closer examination, and from those, after detailed scanning and reconstruction, 4 events were confirmed as genuine tau neutrino interactions, each showing the telltale kink of a tau decaying almost immediately after being produced. 4 events, out of hundreds of millions of recorded interactions, were enough to establish with high confidence that the tau neutrino is real and behaves as theory predicted. The result was announced in July of 2000, and it completed the roster of 3 neutrino types that the Standard Model's 3-generation structure had implied for decades, closing what had been, up to that point, the last unconfirmed particle predicted by the theory's basic framework. The tau neutrino has continued to be a subject of active study since, and not only in accelerator laboratories. The IceCube Neutrino Observatory, a detector built from more than 5,000 light sensors buried deep in the ice at the South Pole, watches for faint flashes of light produced when high-energy neutrinos from deep space interact within a cubic kilometer of ice. Most of the neutrinos' IceCube records cannot be sorted by type with confidence, but a tau neutrino interacting at sufficiently high energy leaves a distinctive signature, sometimes called a double bang, in which the initial interaction that creates a tau lepton and the tau's own decay. A short distance later both produce separate bursts of light, spaced out enough along the tau's brief but relativistically extended flight path to be told apart. In March of 2024, the IceCube collaboration published a study identifying 7 events consistent with this astrophysical tau neutrino signature, drawn from roughly a decade of accumulated data. The collaboration was careful to describe these as candidates rather than certainties, since distinguishing a genuine tau signature from other high-energy events in the ice remains statistically difficult with the sample sizes available so far. But the result stands as the clearest evidence, yet that tau neutrinos produced far outside the solar system, in the most energetic astrophysical sources known, are reaching Earth in detectable numbers, decades after the particle's existence was first confirmed in a laboratory beam. With the discovery, the mass, the lifetime, the decay channels, and the associated neutrino all established, it is worth stepping back and asking where tau particles actually turn up, since none of this happens in any setting resembling ordinary daily experience. Producing a tau requires concentrating a fairly large amount of energy into a very small region, because that energy has to be converted directly into the particle's mass, following the same mass-energy relationship that governs nuclear reactions and stellar fusion. In practice, this restricts natural tau production to a small number of settings. High-energy cosmic rays striking the upper atmosphere occasionally produce particles heavy enough in their decay chains to yield a tau, though this is considerably rarer than the muon production that fills the same cosmic ray showers, since it requires a higher energy threshold along the way, typically through the decay of particles containing a charm quark. Inside stars, temperatures, and particle energies, while extreme by everyday standards, generally fall well short of what is needed to produce taus in any meaningful number, which is part of why the tau plays essentially no role in stellar physics or nucleosynthesis, unlike the lighter, far more abundant electron. The overwhelming majority of taus that have ever been studied were produced deliberately in particle accelerators built for exactly that purpose. After the original discovery runs at Spear, later generations of colliders continued to produce and study taus in far greater numbers. The Large Electron-Positron Collider at CERN, which operated through the 1990s before being decommissioned to make way for the Large Hadron Collider in the same tunnel, produced enormous numbers of tau pairs and was responsible for many of the precision measurements of the tau's mass, lifetime, and decay branching fractions that are still the accepted reference values today. So-called B factories, purpose-built electron-positron colliders, including Babar at SLAC and Bell at the K Laboratory in Japan, which ran through the 2000s, also produced large tau samples as a byproduct of their primary mission studying particles containing bottom quarks, and contributed further precision measurements. The successor experiment, Bell de Secu, running at the upgraded Super KEKB Collider in Japan, continues this work today with an explicit tau physics program aimed at improving the precision of the tau's measured mass and lifetime, searching for extremely rare or forbidden decay patterns that would signal new physics beyond the standard model, and testing whether the tau truly interacts with the weak force in exactly the same way as the electron and muon, a property called lepton universality that sits at the center of some of the more interesting open questions in the field today. Alongside Bell-Decennin, the Large Hadron Collider at CERN, best known for discovering the Higgs boson, has also become one of the most productive sources of tau data in the world, simply as a byproduct of the enormous number of high-energy proton collisions it produces every year. Proposals for future accelerators, including a possible circular electron-positron collider that would run at the same tunnel scale as the Large Hadron Collider, but at lower energy and correspondingly higher precision, have specifically cited improved tau measurements as one of their scientific goals, alongside more familiar targets like further study of the Higgs boson itself. None of these future machines has been approved for construction as of this program, and they remain proposals under evaluation by the international physics community. But their design studies give a useful sense of where researchers expect the most productive next steps in tau physics to come from. That question of lepton universality deserves its own explanation because it connects directly back to the flavor puzzle mentioned earlier, and because it represents one of the genuinely live, contested areas of current research involving the tau. The Standard Model predicts that the electron, the muon, and the tau should interact with the weak nuclear force with identical strength, differing from one another only because of their different masses, not because of any deeper difference in how strongly they couple to the force itself. This prediction can be tested by comparing decay processes that can proceed either through an electron, a muon, or a tau, and checking whether the measured rates match the ratios predicted once the mass differences are properly accounted for. Through the 2010s, several experiments studying the decays of particles containing bottom quarks, most notably the LHCb experiment at the Large Hadron Collider, reported measured ratios involving tau decays that sat somewhat above the Standard Model's prediction, hinting at a possible violation of lepton universality, specifically involving the tau. These hints generated substantial interest because a confirmed violation would point directly toward physics beyond the Standard Model, something the field has been actively searching for since the Higgs boson's discovery in 2012 left the existing framework essentially complete on its own terms. The status of these measurements has evolved since then, and it is worth being precise about where things currently stand rather than repeating the more dramatic early headlines. Some of the related measurements involving decays comparing electrons and muons rather than tau specifically were substantially revised by LHCb in 2023 and found to be consistent with the Standard Model after a more careful accounting of certain background effects, reducing the overall tension in that particular part of the picture. The measurements involving tau directly, generally referred to using the ratios called R of D and R of D star, have remained more persistently, if modestly, above the Standard Model prediction across multiple independent experiments, including Bell, Baybar, and LHCb, though the statistical significance of the deviation, when the results are combined, has stayed in a range that the field considers suggestive rather than conclusive. This is an area where ongoing measurements, particularly from Bell-Decennin and continued LHCb data taking, are expected to either sharpen the tension into something closer to a confirmed discovery or resolve it back into agreement with existing theory. And as of the most recent combined analyses, that resolution has not yet arrived. It is presented here deliberately as an open and contested measurement, because that is an accurate description of where the science currently sits, not because it makes for a more exciting stopping point. This ongoing work sits alongside the broader, longer-standing puzzle already introduced, the question of why three generations of matter exist at all, and why their masses span such an enormous range, from the electron's 511,000 electron volts up through the tau's 1,777,000,000. The Standard Model can accommodate this pattern. It cannot, at present, explain it. Various theoretical frameworks beyond the Standard Model have proposed mechanisms that might generate this kind of pattern from more basic principles. Some approaches introduce additional symmetries among the generations, sometimes called family or flavor symmetries, that would relate the coupling strengths of the electron, muon, and tau to the Higgs field in a structured way, rather than leaving them as three independent, unrelated numbers. Other approaches, arising from string theory and related frameworks, suggest that the observed masses might depend on the detailed geometry of additional spatial dimensions, too small to have been detected directly, with the three generations emerging as a consequence of how particles are arranged within that hidden geometry. A further family of ideas looks for patterns in the numbers themselves, searching for simple mathematical relationships among the measured masses that might hint at an underlying rule, in something of the same spirit that patterns in atomic spectra eventually led to quantum mechanics a century ago. None of these proposals currently has direct experimental support, and they should be understood as speculative extensions rather than established physics, offered here only to indicate the kind of explanation physicists are looking for, not as a preview of an answer already in hand. What is firmly established is the pattern itself, measured to high precision across decades of experiments, and the honest acknowledgement that the deeper reason behind that pattern remains one of the genuinely open questions in fundamental physics. It is worth taking stock at this point of what has actually been established about the tau across all of this, separating carefully what has been directly measured from what is modeled and from what remains speculative, because that separation is the most useful thing this kind of discussion can leave a listener with. Measured to high precision across many independent experiments spanning 50 years, the tau's mass, its electric charge, its spin, its mean lifetime, the branching fractions of its various decay channels, and the existence and basic properties of its associated tau neutrino. Measured, more recently, and with growing precision, the coupling between the tau and the Higgs boson, confirming that the mechanism responsible for generating its mass behaves as the Standard Model's Higgs framework predicts. Modeled, meaning derived from a well-tested theoretical framework and consistent with all data collected so far, but not something that can be independently verified by direct observation in the same way a mass or a lifetime can. The tau's status as a genuinely point-like particle with no internal structure, a conclusion drawn from the absence of any deviation from point-like behavior in scattering experiments down to extremely small distant scales, rather than a positive demonstration of zero size in some final sense. Speculative, or at least unresolved, why the three generations of matter exist in the pattern they do, why their masses differ by such enormous factors, and whether the modest persistent tension in certain tau decay measurements will eventually resolve into a confirmed departure from the standard model, or fade back into agreement with it as more data accumulates. Taken together, this gives a fairly complete answer to the question this program opened with. A tau particle is not made of anything smaller, as far as the best available experiments can tell. It is not a tiny hard object waiting to be cracked open to reveal internal machinery, the way a proton was found to contain quarks and gluons. It is, in the current description, a point defined by a small number of measured quantities, mass, charge, and spin, that acquires its mass through interaction with a field that fills all of space, that exists for about 290 femtoseconds once created, and that almost immediately transforms, through the weak nuclear force, into a spray of lighter, more familiar particles, electrons, muons, pions, and neutrinos, that carry its energy onward in different forms. It is not made of anything in the sense that word usually carries. It is better described as a stable, precisely defined pattern of interaction, one member of a family of three that nature apparently permits, for reasons still not fully understood. Return for a moment to that control room at SLAC in 1974, to Martin Pearl and his colleagues looking at 24 strange printouts, an electron here, a muon there, born together from nothing they could yet name. What they were looking at was never a small hard object waiting to be found intact. It was a pattern in the data, the faint statistical fingerprint of something existing for less than a trillionth of a second, inferred entirely from what it left behind. 50 years of subsequent work at SPEAR, at LEP, at Fermilab's donut experiment, at the B factories, and now at Bell 2 and the Large Hadron Collider, has done nothing to change that basic character. The tau has never been held. It has never been seen directly. It has only ever been reconstructed patiently from its decay products across generation after generation of increasingly precise instruments, and every one of those reconstructions has agreed with the last. Widen the view one step further, and the tau stops looking like an isolated curiosity and starts looking like a single, unusually clear data point in a much larger project, the ongoing effort to work out why the particles that make up the universe take the specific forms and masses they do, rather than some other set entirely. The electron generation builds the atoms, the chemistry, and eventually the observers capable of asking the question. The muon and tau generations, heavier, more short-lived, and by any everyday measure unnecessary, exist anyway, governed by the same equations, produced whenever enough energy is concentrated in one place, and vanishing again almost as soon as they appear. Physicists have spent 50 years learning to read the traces those vanishing particles leave behind, turning a handful of strange printouts into a mass measured to 6 significant figures, a lifetime measured in hundreds of femtoseconds, and a coupling to the Higgs field confirmed at the Large Hadron Collider. What is left unanswered, the question of why this particular pattern of 3 generations exists at all, is not a failure of the work done so far. It is the next line item on a list that has, so far, been answered patiently, one careful measurement at a time. There is a broader habit of mind in this story that outlasts any single number quoted in it. Nothing about the tau was ever obvious, and nothing about it was ever settled by a single experiment. Pearl's original paper stopped short of claiming a discovery, offering evidence and a mass range instead. and it took 3 more years and several independent decay channels before the physics community accepted the particle as real. The tau neutrino took 25 years longer still and required scanning hundreds of millions of recorded interactions down to 4 confirmed events. The tau's coupling to the Higgs field took another 17 years after that to demonstrate directly. Even now, the question of whether the tau interacts with the weak force at exactly the same strength as the electron and the muon remains open, sitting at a level of tension that the field itself describes as suggestive rather than settled. None of these were dramatic reversals or sudden revelations. They were slow accumulations of evidence, each one narrowing the range of what could still be true, and each one leaving behind a number that has held up under every subsequent test. That is a fairly accurate description of how most of fundamental physics actually proceeds, far removed from the popular image of sudden breakthroughs. And the tau's 50-year history is as clear an example of it as exists anywhere in the field.